Take a look at the two problems from last week and their solutions. So one had to do with oceanography about the tides at the Bay of Fundy up in New Brunswick and Nova Scotia. So you'll see below the question, I have the key parts that we will need to write an equation and draw a graph. So based on the problem, my minimum depth occurs at 2 feet. My maximum height occurs at 58 feet. So the midline is going to be the line that is in between those two numbers. So we find that by adding them together and dividing by 2. So 58 plus 2 is 60. 60 divided by 2 is 30. So my midline is going to be at 30 feet. The amplitude is the distance from the midline to the minimum and the maximum. It should be the same. So it is 28. And that works as 30 minus 28 is 2, and 30 plus 28 is 58. The period. So the problem tells us that it goes from low tide to high tide in 6 hours and 12 minutes. To return back to low tide, it's going to take another 6 hours and 12 minutes. So from low tide to low tide will be one full period for a total of 12 hours, 24 minutes. I can create a fraction out of this by making it 12 hours and 24 minutes is equivalent to 2/5 of an hour, which I can then change into one fraction of 62 fifths. We'll see where that comes into play when we get to the frequency, as the frequency is equivalent to 2 pi divided by the period. So 2 pi divided by 62 fifths is 2 pi times 5 over 62, which would be 10 pi over 62, which would reduce to 5 pi over 31. That would be my frequency. And the horizontal shift would depend on whether or not we are using a sine or a cosine graph. So let's take a look at our graph. It's going to sketch it out here. I got a minimum of 2. I got a maximum of 58. And we said we had a midline at 30. So if we start at low tide, we know that in 6 hours and 12 minutes, I'm going to be at high tide. So halfway between there, I'm going to be at the midline, and that's going to be at a time of 3 hours and 6 minutes. So now I can see my increments are increasing by every 3 hours and 6 minutes. So I'm going to be back at the midline at 9 hours and 18 minutes. And finally back down to low tide at 12 hours, 24 minutes. So if I were to graph this, I can see my period. Right there is at 12 hours and 24 minutes. So if I'm using cosine, this is an upside down cosine curve, I'm not going to have a horizontal shift. If I'm going to use a sine, starting here, I would have to continue out to 15 hours and 30 minutes to finish up this sine curve. I would have a horizontal shift because this sine curve starts at 3 hours and 6 minutes. So the two equations that represent this graph, we had an inverted cosine curve with an amplitude of 2, a frequency of 5 pi over 31. I'm cosine, I do not have a shift, and my midline is at 30. I'm doing the sine equation. It's not inverted. And I do have a horizontal shift. So if I'm going by minutes, which I converted my period into minutes, that 12 hours and 2/5. 3 hours and 6 minutes would be 3 1/10, so 31/6. Sorry, 31/10 would be my horizontal shift. 3 1/10 hours. So those would be the two equations that would represent the first graph. On to number 2. So this time I'm given the graph, and again, I want to find these key details. So looking at the graph, my minimum number of hours of daylight in Denver is 9 hours. The maximum is 15, which means my midline will be 12, because that's halfway between, which gives me an amplitude of 3. The period from 9 to 9, so from this point here to this point here is 355 days. I'm going to go in days for this one. My frequency, 2 pi divided by the period, 2 pi over 355. And again, depending on whether you want to use a cosine or sine curve will depend on your horizontal shift. So to write the equation, I've given my period, I've given my amplitude, my equation. I'm going to use the upside down cosine, the inverse cosine, so that way I won't have a horizontal shift. My amplitude is 3. My frequency is 2 pi over 355. No horizontal shift, and a midline of 12. So for part B, find the amount of daylight in Denver on January 1st and July 4th. Well, January 1st is at time 0. So I know there's going to be 9 hours on January 1st. July 4th, I have to use my equation. So looking at the graph, I can see day 172 is June 21st. That is 13 days before July 4th. So my X value is going to be 185. So I'm going to zip over to Desmos, where I have my equation already in. And we said our X value is going to be 185. I see I'm going to have 14.9 hours of daylight, or 14.97. So on July 4th, 14.97 hours of daylight. On to part C. Over the course of the year, during what period of time is the amount of daylight in Denver at least 14 hours? So I'm going to go to my graph again. And I'm going to put in the equation y equals 14. This gives me the horizontal line. So I know that starting here and ending here, all this graph is above 14 hours of daylight. So I'm going to estimate that to 130 and this to 225. And the 130th day of the year is May 10th. The 225th day of the year is August 13th. So going back to our question for part C, the period of time would be 510, May 10th to August 13th. And then part D asks, if you were in Seattle, do you think there would be an amplitude that is less than or greater than the Denver curve? The amplitude would be greater than the Denver curve. The further north you travel, the longer the change in time between sunlight hours and nighttime hours. If you want to think of the extreme of Alaska being really far north and having 22 hours of daylight in the summer and 22 hours of darkness in the winter, you can see that amplitude is going to change drastically from 2 to 22, midline of 11. So your midline of 12, sorry. So your amplitude is going to be 10 as opposed to the amplitude in Denver, which is currently 3. So Seattle will have a higher amplitude. It may only be an amplitude of 5 or 6. Not as drastic as Alaska, but it would definitely be greater than that of Denver. Hope this makes sense. Hope you did well. And don't hesitate to read it out if you have any further questions.